To recap from the work that we were doing on our last set of lessons, finding a derivative is called differentiation. It is an entire subsection of the mathematics that is called calculus. The part of calculus associated with the derivative is called differential calculus. Remember, the rate of change of various applications is the calculus derivative. Context is going to play a role when we're talking about derivative. The definition of the derivative of a function f is another function. We get another function, this one we use the notation prime, so another function f prime whose value at any input that they ask us for, any c value, is this limit, provided that the limit exists. If the limit does exist, we say the function is differentiable at that input value. So there is some terminology, some language that you will be hearing in the future. We've already seen the prime notation, but I want to build on that a little bit. We're familiar that given a function f of x, the derivative is called f prime of x. Well, we saw in our example that we did in the last lesson, we were given v of t, and we wanted v prime of t. So in that same vein, if I give you g of x and ask for g prime of x, I'm asking for the derivative. There is additional notation that we will see in later lessons, but for now, prime notation will work. If I give you a function y, I might ask for the derivative by saying find y prime. So just as in any function, no matter what it looks like, we can plug input values, independent variable values, into the derivative function and find a corresponding output. The output is the slope of the tangent line at the x value in question. We could be asked, for example, to find f prime of 2. That's asking for the slope of the tangent line at input values of x equal 2. I don't just have to feed that function a number. I could feed it a variable expression, just as if I have x going into the derivative function machine, I could have a plus 1 going into the derivative function machine. So we're going to be very flexible in our notation. Don't get married to f and f prime. Let's work an example. This example says find f prime of x if f of x is the function quantity 1 minus x over the quantity 2 plus x. I wanted to work this example because the algebra involved in using the definition of the derivative with a function that is a quotient is a little bit intensive, and so I want to make sure that you have an example like this in your notes. We are using the definition of the derivative to find f prime of x. Remember, the definition of the derivative is f of x plus h minus f of x all over h. So everywhere that this function has an x, this function will have an x plus h. So let's fill that out. We have 1 minus x, so I'm just going to leave an open parentheses, over 2 plus x. When I put x plus h into that parentheses, now I have taken the function f as it was defined and put x plus h in the function machine. So that's this part of the definition of the derivative. Now all I have to do is copy down f of x. This process is identical to the examples that we worked on the last set of videos. So there we are. Now I need to evaluate this limit. Remember, our process is to attempt to factor an h out of the numerator that will cancel with the h in the denominator that's giving us division by zero trouble. So the best I can hope to do is clean that numerator up a little bit and see if I can get an h factored out of it. So the limit, as h approaches 0, I have two fractions in that numerator. Not going to do anything with the h in the denominator. The way that I add or subtract fractions is to find a common denominator. The common denominator for both of these terms is going to be 2 plus x plus h times 2 plus x. Then I'm going to have a minus. And this term will have a denominator of 2 plus x plus h times 2 plus x. So I want to rewrite these fractions where I don't change their value, I just change the way they look, and where I can hope to get one fraction in the numerator instead of two. So this negative needs to be distributed over those parentheses, so that numerator technically looks like 1 minus x minus h. Here is the original fraction. I need the factor 2 plus x to be in the denominator, but I can't change the value of what I started with. So what can I do to anything without changing its value? I can multiply it by something that has a value of 1. This is the same process you used when adding fractions that didn't even have variables in them. We're using the identical process. So likewise, here is my original fraction on the right side of the minus sign. I need the denominator to look like this so that it's common to the other fraction. But I can't change the value of what I started with, so I have to multiply by something that has a value of 1. So there we are. Now I can clean up what's going on in that numerator. Still haven't evaluated the limit, still have to carry down my limit notation. Now I'm going to write the two terms in the numerator as one term with the denominator 2 plus x plus h times 2 plus x. This numerator becomes 2 plus x, that's 1 times both terms, minus 2x minus x squared, that's negative x times both terms, minus 2h minus hx, negative h times both terms. That is this numerator. Now I'm going to subtract from that this product. I'm using brackets and parentheses very carefully. I'm being meticulous about my work. Now I'm going to distribute the 2 through this parentheses. That's 2 minus 2x. Now the x gets distributed, plus x minus x squared. Now the h gets distributed, plus h minus hx. Let's take another step and distribute this negative. And then we can gather like terms. The limit as h approaches 0. Again, this is all over h. And I still have my common denominator, 2 plus x plus h times 2 plus x. Not going to change anything happening here. Just going to copy it down. 2 plus x minus 2x minus x squared minus 2h minus hx. Now I'm going to change the sign of every term in that set of brackets. So minus 2 plus 2x minus x plus x squared minus h plus hx. And there we have it. Now we're going to cancel what we can cancel in this numerator. I have a positive 2 and a negative 2. I have a positive x and a negative x. I have a minus 2x and a plus 2x. A minus x squared and a plus x squared. This is cleaning up quite nicely. Now I have minus 2h there and minus h there. So altogether I have 3 negative h's. And I have a minus hx and a plus hx. This cleans up quite nicely, actually. What my limit looks like is negative 3h over 2 plus x plus h times 2 plus x, and all of that is over h. I do have an h that I can factor in the numerator, but I'm probably going to take another algebra step so it's more obvious to you. We have a compound fraction. We have a fraction in our numerator, and we have a fraction in our denominator. I am going to flip this one and multiply straight across. And I'll write that here. So I'm going to have negative 3h. When I multiply this by 1 over h, which is what will happen when I flip that, I'm going to wind up with h times 2 plus x plus h times 2 plus x. And in that form, I think it's much easier for you to see that I do have an h in the numerator that will cancel with the h in the denominator. So the next step, the limit as h approaches 0 of negative 3, that's all that's in my numerator, and in my denominator is 2 plus x plus h times 2 plus x. Now I think I can actually take h to 0. Let's evaluate this limit. 2 plus x plus 0 times 2 plus x. Absolutely. I have found the derivative function, and I have a repeated factor in the denominator. Hopefully you see that. 2 plus x times 2 plus x. This is the derivative function. Here is f prime of x. You give me any x value on f of x, and you ask what the slope of the tangent line is there, I'll plug it into this function, and I can tell you what the slope of the tangent line is at that x value.